early for my talk. I'm going to talk to you today about imaging in general. So the things that relate to mostly just optical near-infrared imaging, the things you want to be thinking about, let's say if you're using imaging or if you actually plan to use imaging in the future. In this image, this montage in the background, I show a bunch of Hubble Space Telescope images. You've probably seen these before, and they're very picturesque images. Now, the reason they are very picturesque is not because Hubble's an awesome facility. I mean, it is, but it's not the facility itself that has made these awesome images. It's actually the scientists, the astronomers behind the program that actually acquired these images. What they did is they carefully thought about the target, the science question they want to answer. They looked at the Hubble Space Telescope. They chose their target to optimally suit the characteristics of the instruments on Hubble. They thought about the target, how big it is, how big the individual features are. They thought about the wavelength of interest that they're trying to actually capture information about. More or less, what they're trying to do is maximize information content on these images. And that's predominantly the main reason why we can make really pretty images like this. There's so much information in these things because the astronomers have went out of their way and TACs have actually made sure that the astronomers were going to get a lot of stuff from these Hubble images, because Hubble's just a really unique facility and it's very competitive. So this is the kind of thing I would like you to think about during my talk, is how your science can be maximized by the use of imaging. If you don't do imaging, if you do spectroscopy, much of the same principles still apply. What you're trying to do as an astronomer is use very efficiently facilities that are very limited in resources to understand the universe. So the wavelength region I'm going to be focusing on are the visible and kind of slightly into the infrared. The characteristics or the things I'll be talking about are applicable to other wavelengths as well, but they're little quirks. So, for example, in X-ray astronomy, you have these weird, very long telescopes that focus X-ray photons onto kind of weird detectors in the back here. But more or less, an image in X-ray and radio is more or less the same thing. And so a lot of what I will be talking about applies. But I'll be just focusing on this region. I'll cover a few broad topics, starting off with the concept of imaging, capturing information in a two-dimensional sense, and step through different properties, the main things that drive the choice of imaging or characteristics of the facility you want to use. I'll briefly cover the ideas behind image calibration, what you need to do to actually make your images useful. I'll talk about briefly how to measure light on the images, and finish up with a brief introduction on how to make pretty pictures, so like the color images I just showed at the beginning. If you have any questions during my talk, please don't hesitate to ask. So what is an image? Well, it's by definition just a visual representation of something, of data, of anything that is been captured with a camera, telescope, something digital these days. The first image that was actually captured by a device, a photographic plate, is actually shown here. This is the Orion Nebula. And this is the first time that we saw something that the naked eye couldn't see. Before this came about, everything we could see was limited by our eyes and its light collecting power. With the use of telescopes and doing long integration and photographic plates, they could actually see things that the eye could not see. And so that's what imaging is. It's capturing information, photons of light on a two-dimensional screen and allowing us to see things that we just can't see with our eye. Now, as I step through the different properties, there are kind of some key questions that you'll maybe want to think about for your different targets that you might be observing. The first property or topic that I'll cover are filters. So these are just kind of fancy pieces of glass that are designed to block out light at other wavelengths and allow you to focus on a particular wavelength region in the spectrum to, again, extract information about the target that you're observing. So it's kind of the first thing you want to think about when you're considering imaging. Does your science require information at a particular wavelength? If so, then you can go off and look for instruments or telescopes that actually are suitable to capture that information. The other important thing is the atmosphere. So if you're observing from the ground, the wavelength that you're choosing has a lot to do with the atmosphere. There are certain windows, transparent windows, where we can observe, like in the visible wavelengths of light. But there are other issues, such as the background. So the background of the the atmosphere is glowing at infrared wavelengths, and so it becomes more and more challenging to do observations at infrared wavelengths of light. So this is very much about the wavelength of choice. This is a nice schematic showing the kind of the issues that you need to worry about when you're looking through the Earth's atmosphere. We'll start at the bottom here. This is just wavelength from the UV all the way to the far infrared, and the optical is right about here, showing how different molecules, different elements in the atmosphere actually absorb photons of light at a given wavelength. You can see at the UV, you really start to lose a lot of light from scattering of photons in the atmosphere. At the infrared wavelengths, water becomes pretty important, as well as other molecules like carbon dioxide, where you have entire bands of wavelength spectrum that are completely blocked out. So no light from a source at the top of the atmosphere at that wavelength actually reaches the ground. So if you sum all these different things together, you get this thing right here. This is kind of the transparent window, the optical window right here. And there are a few wavelengths in the infrared that you can actually look through from the ground, but it becomes more and more challenging, and you have more and more limited information where you simply just can't do it from the ground. If you consider, let's say, the black body spectrum of a star like our sun, you can see it's peaking in the optical here, but when you push the spectrum of a star like the sun through the atmosphere, even then you're losing information, and so you either need to correct for that or account for the fact that you're missing light from those different wavelengths. In the infrared, again, it gets really challenging. The other complication is that Earth, or the atmosphere, is glowing at these kind of temperatures, and so the black body spectrum of the atmosphere is actually becoming a very big problem. And so from about 1 to 2 micron, even though the tail of this black body is kind of very small, the brightnesses become very bright, and it becomes more and more challenging to actually observe things in infrared. Stuart probably talked about these kinds of issues yesterday during his talk. So if you were to design a filter, though, to cover the infrared, you wouldn't choose one of these dark regions. You would choose something that's more transparent. And so a lot of the infrared filters in particular are actually sitting in these windows very nicely. So there's hundreds of different filters, all tuned to different science cases. Here's a sampling of filter curves in the optical region here from the Gemini GMOS camera. This is kind of the classic, or the more modern filter set in the optical, the Sloan U, G, R, I, Z. The more classic filters were more like U, V, B, R, and I. The thing about broadband filters, and that's what these do, they trace big chunks of the wavelength spectrum. And so they're great at actually getting kind of crude information about the overall spectral energy distribution, the shape of the spectrum of your source, but not so good at getting fine, detailed information. But the advantage with them is that they're relatively quick at collecting enough photons to actually see your target. So it's great for kind of a quick view. There's another set of filters which are called medium band filters. What they do is just kind of break up the spectrum a bit more, break those big broad bands up into sometimes many filters like the ones shown here. These trace out the continuum of your source a lot better, gives you a bit more information. I've been working on a project for about the last 5 or 6 years now called ZForge, where we broke up 2 broadband filters, which are in the infrared wavelength here. There's a J band and an H band, which usually cover this kind of transparent window in the atmosphere. And we broke it up into 5 filters, and the idea was to trace out galaxies as they redshift and trace out the spectrum more accurately to derive a better photometric redshift. You can kind of see it in this image here. These are images, the same object in redshift 2.16 galaxy. This is Hubble imaging zoomed into the target in the center here. But these 2 other thumbnails actually show our medium band filters, the J bands and the H bands. And you can see in this image here, there's actually the source in the center is actually very blue, and the thing up here is kind of green. What's happening is you're not just tracing out the wavelength spectrum with those filters, you're actually hitting emission lines with the medium band filters. So you can see this one little point right here. There's an emission line, an O3 emission line, which is actually hitting the medium band filter, boosting that flux in that little band, and actually causing this color composite image to show these galaxies and almost read off by eye what the redshift of these things are. So that's one feature about the medium band filters. They allow you to trace the spectrum better, and if you have a bright emission line, they can actually see it a lot better than broad bands. The next step in filter sets are things called narrowband filters, where they just take it down a bit more and block out light, all the light except for a very narrow wavelength region that can vary between 8 and 20 angstroms wide. Here's a sampling of some GMOS filters at the bottom here. These are generally tuned to pick out certain emission line features in astronomical sources. Some of the names are listed here. There are tons of filters. There's lots of them. You can just kind of Google different filter set. One thing that I want to caution, though, is that R-band isn't always R-band. So depending on the instrument, the telescope that you're using, even though the filter is called R-band, the response function of that filter can actually vary quite a bit depending on the telescope that you're using. So for example, the Sloan R-band actually has a very low transmission and has a characteristic shape, which is slightly different than the CFHT R-band here. So if you observe an R-band, you need to make sure that it's the same R-band, or if it's not, you need to actually make a correction to compare those two types of magnitudes.
Is it only just R-band or?
All of them, yeah. So the next issue that I'll talk about is field of view of the telescope. This is something that's usually set in place by the telescope itself, though the instruments themselves can kind of work around with a bit to select how large of the region of sky you want to view with your instrument. So the telescope drives it a lot. It's a detector, and of course the science also determine the field of view that you're after. One very interesting telescope that's not yet been built, but it's planned, the LSST, very large 8-meter telescope, has a whopping 3.5 degree field of view. The reason, or the way they could accomplish this, though, is quite involved, and so they have a series of many mirrors. Here's the primary mirror at the bottom, which reflects light to a very large secondary mirror that then bounces it off to kind of a third mirror inside the primary mirror, which then focuses the light up to some lenses and the camera at the middle here. So very bizarre, but they needed to do that to have such a large telescope covering such a large field of view. And actually, there's this cool simulator, which hopefully set running. Which shows photons of light, simulated photons of light actually interacting with this telescope. So light is kind of raining down from the top here. You can see the light is then bounced off that primary, secondary, the tertiary, and then focused up into the camera. Here's a zoomed part of the camera here, and here's the final image screen where the photons are actually interacting with the detector itself. So this is kind of neat. You can actually download this code and install your own parameters for your own setup using realistic properties of the telescope itself to actually properly model the actual photon path for each of your things. I think you can even add sources as well, so stars off source, and see where the light actually interacts with the detector.
So generally how efficient is it, like hit the glass to reflect that light?
Yeah, so the efficiency of the telescope itself, it's pretty high, but I believe, maybe Anthony Horton, you can say what's a typical telescope efficiency?
Varies quite a lot. For an aluminium mirror, you might get 95% reflections. So 3 mirrors. Quite high cube, and then some glass. Lose 0.5%, 12% of each person. Make a ball like it. 4 pieces of glass, I think.
So 70% for something like this, maybe, not counting the glass and other stuff in the way. So yeah, I guess these things aren't perfect, but it's as good as we can do. So the field of view, again, relates to your science. What do you want to do? How big your targets are? There's a whole assortment of things, again, tuned to the telescope. A question? Yep.
Yeah, sure. For the field of view, what about bright targets that are just outside the immediate field of view? How does that, because telescope's not perfect? Yeah,
so that is a problem. Light will scatter in. It can bounce around the support structure and reflect into the actual beam and actually hit your detector. I think for most purposes, if you're not trying to get really low surface brightness, imaging or things like that, then it's generally okay. It's not going to be a big problem.
Do they publish that sort of information with the telescope?
No, but I guess in general, you don't want to observe it next to a very bright source. Yeah, if you have a choice. The glow, the atmosphere glow, I guess, will increase as well about that effectively. Scattered light as well.
Thank you.
Yeah. So here's just kind of a listing of some common fields of view. So Gemini has this awesome thing that gives you a tiny field of view, but gives you extremely high resolution. I'll talk about that in a second. At the other end, you have something like Subaru, which has a large field of view, and the one I just talked about, LSST. These ones are generally special purpose, so a few targets or one target that are zooming in to get it. These are more survey-optimized telescopes like LSST, which are designed to map out large chunks of the sky. There's a concept called a wedding cake, where you have one telescope, let's say, and it's embarking on a large survey. It's going to map out a very large field of view, let's say, over large regions, this orange region on the sky. But what you can also do is spend a lot of time on very small regions, and that allows you to collect more light from them and actually see more faint things, right? More sensitive observations. And so there's this kind of classic wedding cake thing where at the top here you can see very faint targets, but you have to compromise on the field of view. So you zoom into like an ultra-deep survey and spend quite a lot of time just on that one little chunk of sky, and also zoom way out and detect the brighter sources. And it's kind of complementary. You learn about the brightest things in the universe in the large area, but also the faint things as well. So this is quite a common technique for large surveys. The next topic I'll cover is resolution. So this is just the spatial resolution on your images and how it relates to the target that you're actually trying to observe. This is a composite kind of showing, illustrating one of the main limitations of telescopes, or the ultimate limit, I guess, and that's the diffraction limit. So the fact that light has to pass through an aperture of your telescope, and that size of the aperture, the size of the telescope, determines the resolution of your targets on the actual image. This is actually an image of a simulated region with the VLT. So this is with excellent seeing of 0.2 arc seconds. But the object that was chosen is relatively, just a dot on this image. If you use the Hubble Space Telescope, you can start to resolve out features within this region, which are kind of shown here. This is an idealized 8-meter telescope, diffraction limited observations. If you had no seeing, no atmosphere, if you could put an 8-meter in space, this is the detail you would see. And this is, again, a simulation showing what an overwhelmingly large telescope, this is kind of an ELT squared. This is, I think, a 100-meter telescope that is very much conceptual, probably won't happen for a long time. But in theory, if with such a large telescope, and I think it was 80 to 100 meters, if I remember correctly, the diffraction limit would be such that you can see all this information from something that we can see right now, kind of standard observations like this. So it'd be pretty awesome. And this shows you the power of imaging or spatial resolution. Again, you get a lot more information if you have a better spatial resolution, if your science really needs it. So the key things to think about, the kind of main parameter that you want to look up when you're looking at an instrument is the pixel scale. It's simply the arc seconds per pixel, how much angular size is captured per pixel, and that sets the spatial resolution for the image that we're trying to do. It's linked to the field of view, and again, it's driven by a number of factors, including science. This is a kind of neat diagram showing how the diffraction limit varies as a function of wavelength, going along this direction here, the diameter of your telescope or whatever you're looking through, and the effective diffraction limit along the bottom here. So for example, the human eye with a diameter of about 10 millimeters in optical has a diffraction limit about 20 arc seconds. So here I can see, zoom in quite a bit, I'd say, and actually see pretty high spatial resolution. Obviously, if you go to other wavelengths of light way up here into the radio, it becomes a very different regime where the things that you can actually see at a given wavelength are very different, so you can actually zoom well below the optical limit in very extreme cases up here. This is related to the pixel resolution, so the characteristics of the detector you're actually using. So here's some images showing zoomed in the actual detectors. This is like more like something you'd find from your digital camera with little mini filters installed onto each pixel of the detector. Here's a zoom actual picture of a single detector. These things are quite small, but the size of this was carefully chosen by the instrument designer to actually take into account the actual resolution that you expect at the detector itself. So the main limitation from the ground is just the seeing, so the turbulent blurring of the atmosphere, the full width half maximum of the point spread function, which is a description of how light actually hits your detector, dictated or motivated the choice of the pixel size. And in general, the pixel size should be roughly twice the resolution of the full width half maximum. And there's some examples listed here, and these, if you double them, you roughly get the full width half maximum of the point spread function for these things. I'll show in a bit why that's an important thing to do. This relates to AAO, and I think you'll be hearing about adaptive optics later on today, so I'll kind of step through this quickly. There's an instrument on Gemini GSAOI, which is just awesome. It's just this amazing facility that uses a series of lasers to zoom, produce very high spatial resolution over a relatively large field of view. AAO is great for correcting for small fields of view, but this one's tuned to mapping a relatively large chunk of the sky. This is only about an arc minute and a half, but you can see if you compare kind of a typical image of this nebula, zooming in even with another typical image, you can zoom in one step further and actually see a lot more detail with this particular instrument. It's the Orion Nebula, actually. So this is the first unaided image of the sky. The next parameter relates to sensitivity. So how does your telescope, how does the detector, the filter, how much light actually hits the detector and allows you to capture useful information about your target? So this is very much a mathematical thing, so I'll flash up a big equation here. This is how you estimate the signal to noise that you'll achieve if you're observing something. On the top here, we have the signal, so how many photons of light are actually coming from the source that you're interested in. On the bottom here, these are all the things that make it more difficult to actually detect that source. So these are the effect of noise, So the different sources. On the left here, we have, actually I'll step through them as we step through kind of extreme cases. So the first one, if you have a very bright source of light, the top here doesn't change for any of them, but the bottom here, the main dominating source of noise is actually the source itself. So when you count photons on the detector, there's actually a noise associated with that counting process. It's called a Poisson or counting or shot noise. And it's estimated, shown here, the noise from that is just the amount of photons times the exposure time, and you take the square root of that to get the noise contribution from that one source. So for a very bright source, you can solve this and you can see how the exposure time scales by t to the 1/2, the square root of the exposure time. Another more, at the other extreme, if you have a very faint source, in many cases your observations are limited by noise from either the detector itself, so the read noise, or the dark current, which I'll talk about in a bit, or the actual Poisson or counting noise from the night sky itself. So it's bright, and so it makes it more challenging to detect faint things. If you have a faint source and a bright background, then those other two terms, so the detector itself, kind of cancel out or are not important, and the dominating term is actually just the night sky. And so in this case, you say that you're night sky limited, or sky limited, in terms of your signal to noise. So there's another case, of course, when you have a very faint background, where the detector properties start to set the limit. Can anyone think of any case where this actually might apply? Any type of observations where you might actually have a very faint source, but also a very faint sky background? Very, very short exposures. So yeah, if you don't accumulate enough bright sky, then you're not actually dominated by sky, and the properties of the detector become important. Yep, that's a good one. Anything else? What? UV astronomy. Yeah, that's a good one. Space-based. Yeah, it's a good one. Except actually, space is pretty bright. I'll show in a little bit what's actually contributing to this, but there's dust in the solar system that reflects sunlight, and so in the visible wavelengths, the night sky, well, I guess it's always night in space. The space sky is dark. It's darker than our night, but it's still actually pretty bright. And so in many cases you are limited by the sky. Even Hubble's limited. But the way to get around this problem is, of course, what Thimia said, is to actually just take long exposures. So if you have also, let's say, a narrowband filter, I talked about earlier, focused on a single emission feature, you have very little sky in that small little wavelength region. And so you actually end up wanting to take very long exposures to ensure that you're limited by that sky background. Another area where this is a problem is also in spectroscopy as well, where you're scattering light over a broad wavelength region. And some wavelengths, the night sky is actually quite dark. And so in that case, you want to increase your exposure time to tens of minutes, even 30 minutes, to overcome this read noise and actually get to that sky limit. So that's what I wanted to cover on the imaging section. These are the kind of main parameters that I think that are the properties you want to think about if you're considering doing imaging, or if you want to do more optimized imaging. I'll now step through image calibration and briefly photometry. So image calibration, this is just taking raw data and actually making it scientifically useful. I'll just step through a few of the things that you'll need to think about. I believe you'll be working with some imaging later on, and so you'll get some hands-on experience with this stuff. So what do we need to calibrate? What's actually going on? Well, the idea, or the perfect observations, is one where you've actually only collected information about the source that you're after. Unfortunately, we have to use clunky things like telescopes and CCDs to actually do that. They work pretty well, but they're not perfect. And so what calibration is about doing is trying to remove any instrumental effect, get rid of it, chuck it out, cancel it out, so that what you have in your hand, or the data, is just the astronomical source of interest. So the main thing is to remove the presence, any impact of the detector or instrument, the telescope. The other issue relates to that is actually the detector itself. So each pixel on your detector is sensitive to photons, but they're not all manufactured in exactly the same way. And so they'll react differently to photons. To correct for that, you'll do what's called a flat field correction. You want to calibrate your image, though, to other people's work. And so to do that, you need to be on a common system where you describe the amount of flux or light you're seeing on a system that everyone uses. And to do that, you need to take standard star observations to calibrate the images. Astrometry, the kind of study or the use of positional information in astronomy is pretty important, especially if you're taking images to follow up with spectroscopy. And all of this is more or less the same for spectroscopy, plus another calibration to wavelength. And it's also more or less the same for other wavelengths of light. So the first thing that we'll talk about is kind of removing the detector from the actual image. This is a picture of an image, zoomed in region of an image taken with an near-infrared detector. For this, what you want to do is kind of remove the thermal hum, or the imperfections of individual pixels that kind of lead to gross additive offsets in each individual pixels. This is an image showing how the pixels here kind of just immediately have charge in them that is different from the pixels right next to them. And so what you want to do is kind of capture this information and subtract it from your image. And so you usually just take a bias image, or in more infrared detectors, you'll take something like a dark image, which is allowing no light to hit the detector, but you just kind of integrate for the same amount of time as your science observations to accumulate enough thermal kind of hum of the electronics of the detector. Also, during the manufacturing process, you have bad pixels, things that just malfunctioned. And so for these, we want to make what's called a bad pixel mask and actually remove them completely from the analysis. This is a zoomed out region showing a near-infrared detector, showing kind of this is the dark frame. And you can see there's quite a bit of structure. Now, it's pretty low-level structure. The counts here are very low, well below what you'd expect for the kind of typical observations, but still these can have an effect, especially if you're looking for very faint sources. Here's some zoomed-in region showing a bad pixel mask, showing for some reason during the manufacturing process they introduced these kind of, we call it the chicken scratch on the side of Detector 3, which you can kind of model out or subtract right away from the image. So determining how each pixel behaves relative to the next one is related to its sensitivity. To do this, or to correct for this, what you need to do is take a flat field. So this is taking an image of something that's producing, in a spatial sense, an equal amount of photons. So every location has the same amount of photons coming out of it. And so when it hits your detector, each location is roughly receiving the same number of photons, but how each individual pixel behaves differently kind of comes out. And that's what's shown here. This is an image taken of a very flat source of light, so actually the night sky during twilight. And you can see there's a lot of structure, and this is just the pixels behaving a little bit differently. It depends on the wavelength as well, so pixels respond differently at different wavelengths. This is at 1 micron of, and the next image is at 2 microns. And you can see how the pixels behave differently at that wavelength, so it depends on wavelength. This is a raw science image with no flat field correction applied. So you can see the sources of light, but you also see this large-scale structure and also the kind of noise from the flat field uncertainties. This is with the correction applied. You can still see some structure, so it's actually very challenging to produce a very perfect flat field. You can see the kind of big regions out here, but you still got to do your best attempt at that. How do you actually capture a flat field? There's a few different ways. You can have a lamp on the side of the dome wall, use the twilight, or actually use the night sky itself. Ideally, you want to have a source that's kind of uniform in terms of wavelength, and so you can actually correctly account for how this thing varies as a function of wavelength. As I mentioned, though, it's challenging, in particular, to measure the wavelength or the flat fielding corrections you need for a given image. One way to mitigate this uncertainty in your calibrations is actually to take science exposures that are dithered, where you just take between different science exposures your image at slightly different locations. So in these 6 different images, you can see one source. This is a little side-on galaxy in the distance. It's moving around the pixel, the detector itself. And so the photons of light are hitting different pixels. This allows you to correct each image individually, and any imperfections in, let's say, the flat fielding, when you average them out, kind of cancel out to some extent. And so dithering is a great way to actually do that. Once you've actually calibrated your image, you need to just combine the science images the best way you can. As we talked about before, your exposures are limited in duration due to things like the sky background are an issue. When it's very bright at 2 microns, for example, you want to take very short exposures if you're using broadband imaging, like 9 seconds, whereas in spectroscopy, where the sky is actually pretty dark, you can go up to 30 minutes. But there are other reasons why you can't take very long exposures in imaging. One reason is something like this. Can anyone guess what this is?
Moving across.
Something moving across. What's moving across? Not cosmic rays.
Satellite.
Much bigger. What?
Satellite.
Satellite? No.
Moon?
No. No.
That's not moving.
No, it's just all.
Aircraft. Yes, got it.
That's it.
You can actually see the lights kind of blinking on and off as it tracks across the image here. So you got to watch out for terrestrial stuff in your images. What's this? Yeah, I thought it was asteroids, but actually I don't think it's asteroid. It doesn't make sense. And I don't think it's a satellite either.
What's the exposure?
What's two different filters? So you take a green filter and a red filter. It's not a cosmic either. I'm not sure what this is. This might be a UFO.
Well, that could be an aircraft with the port and starboard lights.
Oh, maybe it is. Okay. Oh, yeah. Okay.
Blinking on and off.
That's right, because they have blinking on
Yeah.
Yeah, that might be it.
And they're
Okay.
always on, like it's always just one on. So maybe
one side
you're
is green,
catching,
one side
yeah,
is red.
you're catching the left wing first.
Well, the red and green's pretty clearly matches
Yeah.
port and
So it's
starboard.
probably not solar system stuff, but you do have to watch out for asteroids if you're taking imaging. What about this stuff? What's this? A mess, isn't it?
Pollution.
These are actually the cosmic rays,
Yeah.
and there's a lot of them. Can you guess where this happens a lot?
Towards the centre of the galaxy.
Well, space. Someone said space. I heard a whisper. Space. This is actually Hubble imaging. So this is those pretty pictures I showed you in the beginning. This is what the raw data looks like. It's ugly. It's a pain to work with. This is where it's really important to actually take multiple images so you can kind of reject cosmic rays and actually keep them out and actually do your science. It's remarkable how many cosmic rays you hit in space. Yeah. So cosmic rays, that's another issue why you cannot take long exposures. Another issue is the sky background, which we talked about earlier. So depending on the wavelength of light that you're talking about, the sky is not dark, even in space. So the zodiacal light, which is the one that's dust reflecting off dust grains in the solar system, it kind of sets the limit for the optical and infrared. You then have the glow of the solar system's dust. And in the microwave, you have the cosmic microwave background, and in the radio wavelengths, you actually have the galaxy galactic sources that are setting the background. But you have other things like moons, cities, the telescope itself. Here's some great, I'll just jump to this one. Here's the zodiacal light. There's the galactic center. You can see the zodiacal light there. It's actually quite a big deal. It's quite a bright source of light, actually, depending on where you're looking in the sky. These are some awesome images. They're not coming out too great, but you can actually see there's a lot of color or wavelength structure depending on the elements that are in the atmosphere that are glowing at different wavelengths of light. And this structure varies as well. So this is another period of time, and you can see that the color or the source of emission and the wavelength of that emission changes with time. So that sets one important limit to how long you can take your exposures. So on the one hand, you want to collect a lot of photons without worrying about the detectors, read noise, and things like that. On the other extreme, you don't want to saturate your images, so ruining the brighter sources in your images. You want to make sure that you're not actually saturating the source of interest that you're trying to do. So dithering can help with these things like satellites and stuff like that, but it's still an important issue that you should think about. So you've thought about all these things, you've taken your image. The last step, of course, is to actually combine your exposures, many different dithers, to actually produce the science product. If you had any dithers, you need to correct for that and actually combine the images, correct for the different offsets, which can be kind of a non-trivial exercise to do. But there are many different ways to actually combine things. This is an example showing a raw, uncalibrated image here, just showing the brightest sources. And over an hour worth of an exposure time, I combined 40 images of 90 seconds each, using an average combined and a median combined. And though it doesn't come out very well here, there are subtle differences. Main reason you'd want to use a medium is you want to reject outliers. So if you have, let's say if you have a lot of cosmic rays, you might want to use a median combined to reject them. An average, kind of statistically speaking, increases the signal, or more optimally increases the signal to noise for faint sources. So the next thing I want to talk about is photometric calibration. So we've talked about calibrating the detector to get rid of all the instrumental and detector properties. So now you're just left with information just about your astronomical source in principle. You've combined it all. Now the next thing you want to do is actually start extracting fluxes or information about the source. I'll talk about how to do that in just a second, but before that, I'll briefly touch on how to actually calibrate or correct for the fact that your telescope, the properties of it, are different than the telescope next door. And so you need to correct for the fact that the amount of photons that actually hit your detector is different, even if you're using the same wavelength or the same filter in the actual camera. The way to do that is actually to measure something that's kind of called a standard star. So it's a star that someone has actually worked kind of hard to actually measure the intrinsic brightness of a star as a function of wavelength. So by observing that same star, or everyone observing it, you can actually correct for the differences in your telescope to that common system and actually come up with a magnitude, let's say, that's comparable to someone else's magnitudes. Another important thing you want to do is the astrometric calibration. So even if you've corrected for the dither offsets, you want to maybe put your image onto a common system that everyone else uses to describe where your image was actually taken. So this is called astrometry, where you use maybe right ascension and declination and assign it to your image, and you can build that into the FITS image itself. Astrometry.net is a really quick and really quite remarkable way of doing this. You just upload a random image, and what it does is it looks for sources in that image and uses this very optimized database to look for geometric patterns in the image to actually say exactly where that image is on the sky. And it does it, without any information about the image, about the size or the pixel scale or anything, and it can actually register your image to the kind of global right ascension declination system. So now we're ready for science. We've calibrated everything, and so we're now ready to actually start extracting information about the sources of light on the actual image. Photometry is the study of that, or the study of extracting the light. It depends on the source, and so what I'll talk briefly about is how to measure the source, the brightness of a point source of light, so like a star. If you're working with a big galaxy like the one shown here, you use a very different technique. But even distant galaxies, which you can kind of see have resolved, have structure, require a different technique. But if it's extremely far away, you can kind of treat it as a point source as well. And so the same principles, which I'll talk about, roughly apply. So the objective is to measure the total magnitude of, let's say, that source right there, of relatively faint point sources. You want to maximize the signal to noise ratio. You want to make sure you have a very secure measurement. And so you need to, again, think about what's the noise, what actually contributes to that, and try and minimize that as much as possible. The technique I'll talk about is called aperture photometry. It's quite simple, but it's a very common technique to use. To do that, let's briefly consider what the actual source, the point source, looks like on the images in a couple of different ways. So this is an image scaled so that the center is kind of saturated in the image. There's actually information there, so if I scale it slightly differently, you can actually see that there's light kind of coming in all the way to the center here. You can see a contour plot in a 3D view of that, and you can project that and actually see, as a function of radius from the center of the object, what it is. Now from the ground, the full width half max is usually set by the seeing limit, and so in this case it's about 0.6 arcseconds. And so this is not the characteristics of the object, this is just the actual atmosphere blowing the thing. So aperture photometry is quite simple. All you do is you sum up all the flux in a region centered on the source and subtract off the background. And so you use like an annulus, which is shown here, to estimate what the background in the image is. So you isolate just the source of light itself. Here's mathematically how you do that. The main issue you want to think about, though, is how large to make your aperture. So you can bring it in very closely. If you bring it out too far, though, you'll see that you'll get other objects that start to contribute to the flux of your aperture. And also, if you see something that's quite bright, you actually see the light is actually scattering pretty far away from the center here. So you want to have a large aperture, but you don't want to have it too large because you start to get other stuff in it as well. So there's kind of a trade-off here. Where do you put your aperture, and how do you optimize the signal to noise? So you want to optimum, yeah. So you have to kind of go back to this equation here. Signal, you want to get as much flux from that source as you possibly can. You'll notice from those other images that a lot of the flux is actually right in the center here, so you kind of want to bring it in. Another reason why you bring it in is because the dominant source of noise is actually the sky, and so if you have a big aperture, you get a lot of sky noise in the aperture, and that reduces the signal to noise. So you kind of want to actually bring in the aperture as close as possible. The trouble is, though, that you miss a lot of light. You miss all the light that's kind of scattering to large radii. And so what you do is you correct for that. You do something called an aperture correction. And the way you do that is to actually estimate how much light is falling out to large radii in let's say, a point spread function model. It's hard to see in this projector here, but there's light actually kind of extending out here. And so you can combine a bunch of point sources of light, stack them together, come up with a typical description of how light falls, choose an aperture, and then correct for the amount of light that's falling outside of that aperture.
Quick question, do you account for the artifacts generated by the telescope? Like if you look at your image a couple of slides back, that all those,
These things.
Yeah.
When you combine, let's say, a point spread function model, you effectively get that information of how much light's falling off with radius. In the central regions here, or for this simple technique of aperture photometry, you don't really care about the two-dimensional structure so much. You just care about what fraction of light is falling outside of your aperture, and so then you correct for that. Yep.
When you do your radial profile, it takes into account all of the sort of circular pixels, so that just will give you like a bit of a spread at one time that it happens, so it won't spread down.
Yeah. It won't happen once. All the sources of light on the image will have roughly that same characteristic, but it'll vary with field. So if you have enough of them, you can start to recover that, even that kind of very faint structure, and reduce the noise out here. But you're definitely right. Okay, so yeah, the correction, aperture correction, is just from your aperture in the center, you're just correcting for the light that falls outside of it. And so you need a point spread function model to estimate how much light is actually falling out for that. So aperture magnitudes work for point sources of light. If your sources are varying in size, then the fraction of light falling outside of your aperture will change. So this doesn't really work for spatially resolved galaxies. You then need to account for the fact that galaxies have different sizes and try and capture the information, again, in a very optimal sense, without compromising the signal to noise, but trying to still get total magnitude for that source. So I'll just wrap up with a brief intro on how to make pretty pictures. Pretty pictures are fun, they're engaging, the public like them, I like them, you like them probably. They're also scientifically useful. So I actually discovered a Redshift 2 galaxy cluster by just looking at this image right here. I saw this clump of red things and I thought, hey, this looks interesting. And sure enough, we've embarked on this big, 15 paper follow program just to follow this thing up with like 15 nights on Keck. And I just found it by looking at a color pretty image that I made. So it's scientifically useful in certain cases. They're relatively easy to make, so I encourage you actually to try and do this. DS9 is a handy imaging viewing tool and it has some of those capabilities. You can use Python as well to kind of fine-tune it. I don't have time to go through these, but these are, again, my Z-Forge galaxies showing HST and then my medium bands here. You can see there's information. The galaxies, you can actually see their SCDs or their spectral properties as a function of wavelength in these RGB images. DS9, you can actually load up 3 separate images, 3 separate channels, and actually produce a color composite here. And that's what I use to actually find that Redshift 2 cluster. Here's a bit of code, a command line code to actually load up 3 separate images into the 3 channels. There's a cool set of command line commands or utility called XPA set, which sets DS9 up to actually make a kind of right out of the box pretty functional, pretty useful 3 composite image that you can zoom around with. If you want to use Python to really fine-tune it, here's some code. I think you'll have a chance to do this later on in the workshop. And I'll just finish up there and take any last questions. Thank you very much.
Thank you, Lee, for that very thorough overview of all the concepts of imaging and making measurements from those images. Questions?
If some of the averaging techniques give you different benefits, would you then consider doing like an average of all the types of the averages?
I think that this worked because you're using the same data more than once. It's like you should only use your data once. You shouldn't add the same bit of information again and again. Because it adds error. Yeah. I mean, you could do it as a function of do like 10 different techniques and see how your choice of technique influences the final measurement.
Yeah.
So it's kind of like a systematic uncertainty on your imperfect ability to combine scientific exposures. You can use more fancy techniques called drizzling, which kind of mitigate some of that effect. But yeah, that's a great idea if you want to kind of characterize the uncertainty as a systematic uncertainty. Yeah.
Other questions? Well, actually, I come back to what Lee was saying at the beginning. I think for many of us, we often make this distinction. We say imaging and spectroscopy, almost as if they're two different things. And yet, if you think about it, the type of work that Lee was describing, he's been doing is imaging. In many ways, is just very low resolution spectroscopy. Right? The resolution power maybe only 10 or 20 or 100 or something. Yep. But that's another way of thinking is that imaging is really nothing more than a low resolution spectroscopy mode of analysing the data.
How many of you do imaging? How many do spectroscopy? How many do theory?
Wrong workshop.